All right. Thank you for coming today. So, yesterday in the keynote, we showed this demo. It was done by Nordius, and it's all about how you can do massive scale simulation in Unity. And this talk today, it's really about digging into the details of how we can write such code and how we can get this massive leap of performance. So in this demo, we can have 100,000 units. We can spawn them at a really, we can have these 100,000 units simulating every frame. We can instantiate objects. When I blow these units up here, we're basically instantiating new units, destroying old units. We're not allocating any GC memory while doing that. It's barely noticeable on the frame rate when all of that happens. And in this talk, we're really going to dig into some smaller examples of how we can do those things with Unity. So let's start with why is performance important? So I think performance is an enabler. You can do a lot of things with performance. One thing is just build something like that. If you want to make a real-time strategy game, you can have a massive amount of units on screen if you have great performance. Or you could use it to do more detailed simulations, write more complex code, more complex AIs, these kind of things. Or maybe you just want to run at 60 frames per second, spend less time running your game code on the main thread. Or maybe you're just making a tiny game for a mobile phone and you want to save battery consumption. Performance can simply be used to run your frame instead of taking 32, 33 milliseconds, you just run it in 6 milliseconds, and then the rest of the time the CPU is idle. And that's what reduces battery consumption. So, sorry. The basics of how we get to having great performance comes down to really 4 things. So the first one is we need to really have good control over memory layout. And we want to walk our data linearly, and we need to have a way of doing that. We want to write multi-threaded code so that we can take care of all these cores that modern machines have. And we want to write code that is automatically vectorized so that all these modern instructions where computers can basically process multiple of pieces of data on a single CPU at the same time so that we can take advantage of that. And we can do that with our C# job compiler. But to take advantage of it, we have to change the way in which we write our code. And that's what we're going to talk about today. So let's talk about the very basics of how to achieve performance. So most programmers grow up with writing object-oriented code. And my belief, I guess it's not a belief, basically I think that when you write object-oriented code, there's a limit to the performance that you can achieve. It's very important to if we want to get to this upper end of performance, we cannot write our code anymore that way. And I'm going to try to explain why that is the case. So to do that, we have to understand a little bit about how a CPU actually works so that we can work ourselves all the way back to how we're going to write that code that is super efficient. So CPUs read data in cache lines. So let's say I just want to read a number. I want to read an int, and I want to use it. It's somewhere in a class or a struct. What happens actually is that the CPU reads 32 bytes or 64 bytes, depending on the size of a cache line, and reads it into memory. It can't read something that is smaller than that from RAM. And so if you read a single float from a random location in memory, and then you read from somewhere else, you're effectively loading 64 bytes of data, and you're not doing anything with the remaining data that has to be loaded as part of that. And all of that is not really visible when you write code today, because that would be pretty complicated. So that happens behind the scenes. But if you don't know that that is happening, then it's very easy to write slower code. So the second fact of modern CPUs is that reading a cache line from RAM takes roughly 100 to 300 cycles. And that means we can read, we can access, like if we try to read a float from a class or something like that, then at the time where we access that float, at that time, we have to wait 100 to 300 cycles if it's not already in cache before we can use that data. And if you do that for pretty much every float that you access, then you're going to get pretty poor performance. So what you want to do is you want to take advantage of the hardware that can do that in parallel to you, to your game code actually doing actual work. So what CPUs do is they have a hardware prefetching unit built in. And that means if we read data linearly, we can take advantage of the hardware prefetching unit to basically do that in parallel while we're processing our data. So the CPU automatically detects, hey, I'm reading a float here, and then there's a float right after that, and then after that, and it just keeps prefetching the next couple cache lines, and they're coming in while you're basically running your code. And that can give you some pretty massive speedups when you take advantage of that. So the question is, now we have that knowledge, what does that mean? Like, what does that really look like when we write object-oriented code? So let's take a look at this very simple example. So we have a class, and we have a string in here, we have some array of ints, some values, we have a quaternion, a position, and of course that all takes memory, right? A pointer, this is essentially a pointer to the string, takes 8 bytes. This one also takes 8 bytes, a quaternion. There's 4 floats in there, so that's 16 bytes, and this is 12 bytes. So the problem here is that this is a class. So when you create a class in C#, that allocates memory in a completely random location in memory. And when you then iterate over those things, for example, you put them in an array, right? So now we have each player data allocated, one here, another one over there, and a third one over there. They're in an array. The pointers to that are linearly allocated, but they point to different locations in memory. And so when we just want to, for example, we have an array, and we want to find the player which is closest, or which is close, within a 0.5 radius. So we just want to calculate the distance between each one, and then return that one. So if we do that, what happens here is that at each array index, we're taking that pointer, and then we access a completely random location in memory. And we're jumping to that. And that's the point where that cache line has to be loaded in to load that position. And in fact, we're not only loading the position, we're going to load 32 bytes of data. So basically, all of that data. But when you look at that code, we're not using any of that data. We're just loading it, and then it's in cache, and it wasted bandwidth on our CPU, but we're not using it. So we're writing really inefficient code from a bandwidth perspective. So what's a better way of writing that? So fortunately, in C# you have structs. If you put a struct in an array, that will be a linear block of memory. And now we have 40 bytes of data for this struct. We still have some pointers in here, some 8 bytes, 16 bytes for the rotation, and so on. So it's a pretty fat piece of data, but at least the memory is laid out linearly. So if we have this loop here now, and we go over these players, and we check the the distance to each one, then basically we're going to read the position, and it's here, and we compare it, we do some math on it, and then we go to the next one. And that comes at a very fixed interval, right? Like 40 bytes after is the next position. So it's a very predictable memory layout that we have. And that means that the CPU can do that hardware prefetching for us automatically. You don't have to do any of that yourself. That just happens. And it happens because you laid out your data completely linearly. Now, there's still a problem with that. I mean, it's great. We're not jumping around in memory. That's the most important thing. But the problem is still we have waste, right? We're reading this position. That's the only thing we're interested in this loop, that we want to be fast. But we're also reading the data for the rotation, the value, the name, all these things. So now we can do what we call a hot-cold split. So basically, we just say, let's just separate those two arrays. Let's take our array of player positions. So that's just 12 bytes per element. And then we have our player data. Let's call that the cold data. That's the data that in our inner loop, we don't actually use that data, right? Like we are only interested in the positions in our algorithm that we want to be fast. And so we just keep those two arrays in parallel, and we just maintain that data that way. So now iterating over the player positions is going to be really fast, because basically we read 12 bytes, and then the next iteration, we are right there, right after we read the next 12 bytes. And there's no waste anymore. We're doing completely linear access without any waste at all. And basically, this, compared to this, we are basically, let's assume we have a 32-byte cache line. We're reading 12 bytes. So we have roughly a 2.6 x improvement in the bandwidth that we consume. All right. So that's the basic idea, right? We want to have control over our memory, and that is how we get performance. That's a very different way of programming compared to how we usually do things object-oriented. There's also a couple other things we want to avoid. We want to avoid virtual functions. We don't want to have like an object that sort of like has a virtual function and an update method, and then in the update method, we basically jump to a vtable where it figures out which function to actually call, and we can't inline the code, all of these things. We want to avoid that. We want to think in batches. We want to think about how do we process a bunch of units that we have, and how do we make that run really fast. So we want our memory to be tightly packed. We want to have linear memory access. We don't want any GC allocations at all. In fact, when we have the game running, basically spawning 20,000 arrows, there's not one GC allocation. And essentially, in order to get great performance, we have to stop thinking in object-oriented programming patterns. We have to think about things data-oriented design. That's how game engine programmers call it. And the new entity component system is all about making that as easy as possible, right? Because it's important for us to make sure that that is easy, modular, and you don't have to spend a lot of time writing that code. So let's take a look at how that actually applies this kind of philosophy to writing code in the entity component system. So there is, let's take a look at a very simple example. That example is basically, we want to rotate a cube. Very simple, right? We basically have a mono behavior, we have a speed value on it, And then we have our update method, and in it, we apply the rotation, and then we calculate the quaternion, multiply it, and now we have a rotating thing, right? Looks something like this. Just have these 4 things that rotate. Each one of them has a speed value, and then by that it rotates. Let's say we want to achieve that. And we want to do that at massive scale, and we don't want to pay much performance for it. So in a new system, the way we can change this kind of code is like this. The first part is basically separating things into 2 parts. First of all, a component contains data. And a system is responsible for having behavior. So essentially we're moving the update method out of the mono behavior, and we're moving it into a system. And the system is responsible for iterating over all these components. And when you look here, there's a get component call. And that's kind of the key question. What do we replace that with when we just deal in data? And the idea is we're just going to populate 2 arrays. And these 2 arrays, each index refers to the same game object or entity. So at index 0, there's my first entity. And it has a transform, and it has this rotation speed component. And these 2 arrays are automatically populated for me. I don't have to write any code, and we have really efficient code that populates them for you, and you don't have to worry about it. And then you just write the system code. So you just have a loop where you iterate over all the transform components, and then you access them at that index, and you access the rotator. So you take the rotator speed, and you use it to rotate that transform component. Okay, so that's cool. Now, we don't have any, we're still storing sort of like object-oriented data. We have a class here, but at least we're doing things in batch. And that's good, because there's no virtual calls to call our update method. And that alone gives us already a speed up. And personally, I also think this is a nicer way of writing code. I think it's more flexible to actually separate the behavior from the data that you want to define. So that's the first step. The second step is that we have a new component type that we can create. So we can create what is called the iComponent data. So an iComponent data is a struct. And in this case, the only thing we have in it is a speed value. Because we want to make sure that there's no overhead at all from the system and the entity system around it. We want to make sure that one float comes one after another, tightly packed. No overhead at all. And when we write that code, the only thing we change now, compared to the previous example, is instead of using component array for the rotation speed, we use component data array. Otherwise, it's exactly the same code. We basically turn this one into a struct, and this one we use component data array to access it instead of component array. And now the data is completely packed. So basically, these speed values, we're accessing them in the most efficient way we can. And that's a really good step. All right, so let's take a look at one more thing. So how does that work when you work in Unity with scenes? So for the time being, the entity component system is actually completely written in C#, because we still want to experiment a lot with these concepts, come up with new APIs, and keep on changing it. When we ship it, we're going to ship it first as an open source GitHub project, and we'll allow contributions and these kind of things, just because we want to have more time to really figure out these new concepts. And what you see here is there is a game object entity component. And that thing is responsible for basically reflecting the data from the old component system into the new one. So everything that is on this game object is visible to the component system. And it's basically visible in these component arrays. So if you say, I would like to have transform and rotation speed, if you have a game object entity on those game objects, then they will show up. And the rotation speed component is here, of course, and that just stores the speed at which we rotate. And looks like this, right? Simple. Okay. So the most important thing is iteration. And we offer a couple of different ways of iterating over these arrays. One is using these tuples. We have an attribute, inject tuples, and Unity then knows what it is, and basically we're expressing the following. We're saying, I would like to have a group of entities that both have a transform and a rotator data on it. And you can put as many as you like. You could put another one here. You could just say, like, okay, I would also like to make sure that it has a rigid body. And now you can, in these arrays, they're going to be populated, and it will only contain entities that have all three components. Okay. Another way of using the API is to use what we call the component group directly. So you can simply specify, okay, give me everything that has rotator data and a transform component. So this basically specifies the components you require, and then you get back a group, and from the group, you can then get the arrays. So you can get the component data array and the component array. And then you can iterate over those and do whatever it is you wanted to do. And the rotator data is laid out completely linearly in memory, while if you use a mono behavior, it's still classes. They are all over memory. But it's a good way to slowly transition code from the old way of doing things with a mono behavior into the new one. You could just one by one just start by moving your game code into systems, and then after everything works, you could move some of them into a component data to get even better memory layout. Okay, so that's basically iteration. That's what you do most of the time. That's where most of the time is spent in a frame. Then we have creating and destroying entities. So you basically use this thing called the entity manager. The entity manager owns all the entities and components in the system, and it manages the memory for you. And you can just tell the entity manager, okay, I would like to instantiate a prefab. And what it will do is this is actually a fast path. Because if you have any I-component data on that prefab, it will extract all the I-component data components on that prefab at the root game object, and it will instantiate those. So basically that way you can use the prefab workflow to set up all your settings and so on. And then you can take advantage of this insanely fast path for instantiating a lot of objects. So we have done some profiling on that. If we run this loop here, we have 4 components, 320 bytes of data, and if we call this function 100,000 times, it takes 26 milliseconds. So that's magnitudes faster than what we have with the game object system. So if you can represent the thing you want to do as a single entity, then you can put everything into a component data, and then you can get massive speedups. And that's exactly what we use in this demo. All of the entities you see on screen, or the arrows, all of these things are single entities, and they use instance rendering to draw it, and there's actually no game objects for these characters that are running around. So we can do that, and we get a really good good speed out of it, right? So we just call instantiate, it extracts a component out for us, and then if you want to, you can also tell in the entity manager, you can say set the component data for that entity to some other value, something like that. It's basically the same as calling get component and then setting a value in the object-oriented way of doing things. Now, one thing is that you want to make sure that, well, we want to make sure that we can really scale. And that often means creating APIs that are accessible by batch. So all of the APIs where we can get speedups like that, we give batched APIs, meaning if we want to instantiate 100,000 entities at the same time, we can make that several times faster than this already really fast way of instantiating instances. And the way we measure how fast it is against the fastest thing you can possibly do. So a memcopy basically copies memory purely. That is the fastest thing you can do. There's no way you can beat it. And I think, since we're rewriting this thing to get great performance, we might as well measure ourselves against what is the theoretical limit. And for instantiating this amount of data on my computer, it takes 9 milliseconds, and a memcopy takes 7 milliseconds. So we are 20% within the limit of what is feasible on any CPU. So there's extremely little overhead to doing this. And that's great, because essentially it means you don't have to worry about spawning pools if you take this approach, because you're just going to instantiate, destroy objects, and you get great performance. There's all kinds of other APIs. You can destroy entities. Destroying entities is also really fast, 7.6 milliseconds if you call it one by one. If you use the batched API, it's 0.9 milliseconds, so barely noticeable. You can add components at runtime, remove components. It's a different API, but basically the same concepts. And of course, if you have an entity, which is basically just a struct, an ID to that entity, you can just call set component. And then it will set the component value to a different value. So let's talk about memory layout. By default, the memory of those components is laid out so that if you have component 1, 2, and 3. Component 1, basically we allocate chunks of 64 kilobytes of memory, and we just lay them out one after another. That's a really good default if you want to get really awesome performance. Sometimes, when you're iterating over lots of data, you actually want to merge multiple components together again, because you might create tons of tiny components because they now have very little overhead. So you start separating out your components out. But then one thing that can happen is you might be accessing too many of these component arrays at the same time when going over one unit. And that can sometimes be bad for performance. So we give you full control over how the memory is laid out. So you can say, okay, I want component 2 and 3 to be packed together. So basically, entity A has component 2 and 3 packed together, and then comes component B. So you can really control everything in the system with regards to memory layout, and that can mean some really, it's a good opportunity to optimize your code, and most importantly, you can do it without changing your code. You just, at the end of your project, you just tweak the memory layout, and you get a bit of speed up from it. And the component data is also always kept in this linear order for iteration. Let's say we destroy an entity. What we actually do is we fill another entity into that place so that we always have completely tightly packed data. And because we can copy the data so quickly, this destroying and creating of units is still extremely efficient. But the main thing is iteration is always kept super tight. Okay, so that's the basic overview of the entity component system and how that applies. Now, the next part is about using our job system and container libraries. Because of course, sometimes you want to use arrays, hash tables, these kind of things. And you want to write your code jobified so you can take advantage of multiple cores. So we'll take a look at how that works. So the first thing we're going to look at is native containers. So like I said, we don't want to write code that allocates GC memory. We want to manually control that memory when we want to write multi-threaded, super high-performance code. So we can create an array, a native array, and we say, okay, we want a native array of int, and we want to have 100 elements. And then you can specify what type of allocator you want for it. We have 3, and these are the same 3 allocators we use in our C++ engine side. So temp allocation are allocations that are released when the function exits. So it's basically a stack pattern, and it reuses that memory constantly. And it's really, really fast, and it's really good for that pattern. Temp job is memory that should not live longer than 1 frame. Very often, we have data that is allocated in one system, and then you schedule a couple of jobs, and then maybe the last job deletes that data. That's a quite common pattern. But it lives for maximum 1 frame, and that means we can make a specialized allocator, which is lock-free, and as a result is really, really fast for this particular pattern. Persistent memory is memory that goes through a normal memory allocator that is basically similar to the built-in malloc you have in a system. Using that array is the same as using a normal array in C#. You just want to assign a value, that's fine. You just assign the value. What's different is you have to dispose it. It's manual memory management. You're responsible for disposing the native arrays. What we do have is that we have leak detection. So automatically in the editor, when you allocate a native array, we track that, and if you no longer reference this array from anywhere, but you forgot to dispose it, then you get a nice error message pointing you to exactly where it came from. So you can very, very quickly find these leaks, and they usually don't fall through the cracks, unless you're not watching your console window, of course. So we have several different useful container types: native array, native list, native slice, which lets you basically take a subpart of a list or an array. And native list works basically the same as a normal generic list. So you can add, remove elements, all the functionality that you expect from a list. And you have a native hash map to do really optimized hash table lookups. And we have a multi-hash map as well, so that you can have multiple keys and different values. The same key and different values. And of course, these container libraries are written in a way so that you can use them from multiple jobs. So for example, a multi-hash map, you can write to it from multiple jobs, and we use atomic operations to very efficiently insert the keys into it. Okay. Next question is, what does a job look like? So a C# job looks like this. You basically create a struct, and in the struct, you put the data that you're going to access in the job. And that's really important because the job system has to know what data you will access inside your job in order to make it safe for you. One of the key parts of this job system is that it makes it impossible to create race conditions in this way of writing code. And that creates simplicity that makes it feasible that you can actually use this to write a lot of game code. And because of that, you have to put all your native arrays that you're going to access from the jobs into the struct. So you can't access global variables, for example. And you also can't put a reference type in here. You can't, for example, do this. There's a reference type, and you can't put it in there because the C# job system cannot make sure that the usage of that is completely safe. You also declare how you're going to use it. So you're going to say, okay, I'm only going to read that data in my job. And by default, something is readable and writable. So in this case, we are simply trying to copy an array of floats. Right? That's maybe the first simple job you want to write. So we have an array of source data and destination data, and we just loop over the array, and we assign to the destination from the source, and then we multiply by a value. So you fill out the struct, and you implement your execute function. You schedule it on the main thread. So on the main thread, you create a copy floats job. You fill in your arrays that you allocate manually. Maybe you want to have a delta time. You can't call time.deltaTime from a job. A job doesn't have concept of a frame. Right? It might be next frame, in which case the delta time might change while the job is running. So you have to put all the values that you're using in the job into the struct. And then you simply schedule the job. So when you schedule a job, you get back a job handle. The job handle is basically a thing you can either wait on or you can use it as a dependency. We'll get into that in a second. So if I write something like this, right? Now we're scheduling the job is running on another thread, and there's no guarantee on when it will execute, right? Might be now, might be next frame. So if I write to this data, the source data that we're copying in this line, if we do that, then we're overwriting data that the job is reading from. That's clearly a race condition. We can't do that. And when you do this, in fact, Unity will give you an error message, and it will tell you this is invalid. You need to change your code. And if you want to fix that, and you actually, for some reason, do want to write to that data, then that's fine, you can do that. You just call jobhandle.complete. And that ensures that your job has completed at that time. And now you can write to this data, and you know the data has been copied. Like basically, the destination array has been filled with the same data that was in the source array. So that's the guarantee we make. We also have different kinds of jobs. We have, for example, a iJob parallel 4. An iJob parallel 4 basically can be parallelized over multiple cores. It basically splits the work into chunks, and it makes the assumption that that this loop doesn't access sort of like randomly into these arrays. So for example, we are doing the same thing, which is copying at the index. Right? We're taking from the source, and we're writing to the destination. So the code actually gets simpler, and of course, it gets distributed over multiple cores. What we can't do is, for example, write to index 0. Right? Now there would be multiple jobs writing to that index. And of course, again, we have a safety system for that. So if you did that, you get a nice exception telling you what you did wrong. Okay, so we can fill out the job data again, schedule it, and then we specify over how many elements do we want this parallel for job to iterate. So basically, this execute function is going to be called with every index between 0 and 500. And the second parameter here is sort of a batch size. So basically, there's an inner loop that this job like there's code generated for you that has an inner loop, and that inner loop basically just has a tight loop of 100 elements at a minimum, unless it's, the array is smaller than that, of course. But basically, to make it so that you can really have very little code in the execute function, and the code in it is still really fast because we just have that loop for you. Okay, so that's iJob parallel for. That's a really common one to use. Almost all of the game code in the Nautilus demo that we showed uses iJob parallel for, because we want all the game code just to process wide on all the cores. We had our 18 different worker threads running at the same time, so we want each one to just always do work. Okay. The next really important thing is dependencies. So one thing that commonly happens when you start writing multi-threaded code is you schedule a job, then you wait on the job, then you do some more work on the main thread, and then you schedule another job. And what happens when you take this kind of approach in multi-threaded programming, then you're basically doing work in parallel, and then you're waiting on the main thread, and then nothing happens on the worker threads. And then you schedule another job, you're waking up all the worker threads, and then they do some more work. And essentially with this approach, you can never really get to full multi-core utilization. You just see these blocks of going parallel, and that's cool, but it doesn't really get us all the way to great performance. So what we need to get to solve that problem is we need to introduce dependencies. So if we schedule a job, we get back a job handle, right? And instead of calling job handle complete on the main thread, we can simply schedule a job and say, we want that job, that second job, to only run once the first one has completed. So in this case, we're copying an array from 1, we're copying a source array to a destination array, and then we're copying the destination array again to a third array. And we don't want the second job to start executing until the first one has completed. So basically, we just fill in the arrays the same way. We schedule the job. We have the job handle A here. We create another array. We fill in that one with the destination of the previous job. And then we copy to the final destination, where we copy this memory to. And then we schedule the next job with a dependency on the previous one. So now, when we wait for job handle B, then it will wait on both of those jobs. So it will guarantee that both jobs have been completed, and they have completed in the right order. And with that, you can express very, very efficient multi-threaded code in a very simple language, so to speak. In the demo we were showing yesterday on Tuesday, we're using we have roughly 18, 19 different jobs, and we have, I believe, only 2 sync points on the main thread. Sometimes you need them. Sometimes you just you just don't have enough time to make it perfect. But the point is, you can express those things with dependencies, and it's always good to prefer dependency over just waiting on the main thread, and just let those cores do what they're best at. All right. So let's take a look at what happens when we use these jobs in our entity component system, how that actually looks in practice. So last thing we looked at was this way of writing the rotator, right? We have a component data array with a rotation speed. We're rotating, we're doing things in batch. And once we have this way of writing our code, transforming it into multi-threaded code is actually pretty simple. So what we do is instead this. We have a job component system. So instead of using a transform, a component array of transform, we're going to use a transform access array. And the transform access array is a way of using the transform component from a job. That's what this is for. And we can use the same inject tuples logic on that. So we just replace that component array to transform access array. And this one already uses a component data array, so we can use it on a job. Then we write the job. So first, we put our delta time in here, because we can't call time.delta time on a job, of course. That's a global variable. And then we have our array of rotators that we want to execute over. And for each iteration that we do, we get past the transform axis, which we can rotate with. And the index, similar to the iJob parallel 4, we get the index of the element we're supposed to process. So we just change the rotation, and we multiply by the angle axis. Same code as here. This is literally the same line of code, right? I mean, basically, just change this one to be the transform. And when we schedule it, we give it the array of transform components, and we put the array of rotation speed onto the job data. And that's it. Now we can schedule our job. There's two more things with that. So when we looked at the example with scheduling a job and dependencies, we basically, here we are manually tracking these dependencies, right? We return a handle, we give it to the next job, and so on and so forth. But we want to write modular code. And of course, if I have this rotation system, maybe I have another system that modifies in a job the rotation speed. And of course, we want to make sure that that rotation speed is being changed from that job before our system rotator executes on a job and then changes the, uses the rotation speed to animate the transform. Right? We want to write that in a modular way because these two systems, maybe they don't know about each other. Maybe that's something somebody else wrote. So basically, the job component system gives you these two functions, add dependency and get dependency. So because you put this inject tuples on these arrays, because of that, when you schedule a job, it knows you're reading from rotation speed. Cool. We're going to take the dependency that the system automatically tracks for us, and anyone who's writing to the rotation speed, we need to wait on those before we execute the job. So that's basically the dependency. So it collects all the dependencies that you might have because you declared these tuples and uses them. And then after you have scheduled the job, you have to tell the system back, I have scheduled a job. And in fact, I was reading this rotation speed value, and I was writing to the transform component. And the add dependency tracks that for you so that the next system that maybe then wants to use the transform or something like that can depend on it. So that's how a job in the new, when using the new job, the component system looks like. And the data is really simple, right? We have just an I component data just containing our speed value. Okay? All right. Yes. yes, let me show you one more thing. So I want to show you what happens when we make a mistake. So let's say we oh no, shit. Oh. It's not in alpha yet, so I guess it's okay. So let's say we make a mistake with one of our jobs. So, for example, I have this collision system here, where we basically do rigid body, like we just do raycasts to figure out where these guys hit. Okay, so let's say we just remove a dependency on the second job here. So we just forget this dependency, that it was necessary. So just run that. Jesus. Wow. Cool. It's a beautiful error message when it comes. It's actually, it's probably in the console log now, so we can just look at it there. Wow. I'm so sorry. The point was, basically what it says before it crashed is this. It says, the previously scheduled job, batch query job, reads from the native array, batch query job commands. And you're trying to schedule a new job, collision minion system integrate position, which writes to the same native array via integrate positions raycast. To guarantee safety, you must include batch query job as a dependency of the newly scheduled job. And when you get your hands on it, it's not going to crash just after, which would be amazing, right? And I am really surprised it crashes now as well, because it's been pretty solid while we were making the demo. But I guess that's how it goes in stage demos. So we have these safety systems, and I think the safety system is actually really one of the key features of this system, because writing multi-threaded code is difficult, and it's difficult because creating race conditions is so freaking easy. And if we want to make it so that a lot of people, a lot of developers start writing multi-threaded code, then we have to make sure that you can trust the system. Not like that crash. Like actually trusting it. And so this system really detects every possible race condition that you can create, so that you can just change your code last minute. Like, for example, in the demo that we made a couple days ago, before the keynote, we were running at 45 frames per second. And there were several sync points left on the main thread that were really just creating big holes in the frame because we were just waiting on these jobs too early. And so we decided to just change it around. And nobody knew why there was a .complete call. I mean, at some point, the code got refactored, and then it wasn't necessary anymore. So we removed it, and turns out we forgot a couple dependencies. System tells you exactly where they need it, and then you add them, and then it works. As opposed to the system just crashing at a later point because it's overwriting some memory. And that's a really key part to getting more people to write this kind of this kind of jobified code. So there was one more thing I wanted to show you a bit. There's, let's take a look at sort of the simplest way to write a job in the new system. So let's say you have this thing, like we were basically exploding these rigid bodies, and when they are exploding, then we just make them fly through the air, cast a ray, and figure out where they hit the ground. And this is the job that performs the gravity calculation. And what we're trying to do here is make it so that you don't even have to schedule the job yourself. You just write the job code, and you use this iAutoComponent system job. And what it does is, on the main thread, it gives you a prepare method. So here we can extract delta time or gravity, set up any values that we need in this job struct, and then you get an executes function where you simply get the reference to that specific minion. And you can have 2, 3, 4, 5 different components here, and they basically refer to the same entity that we're processing. So that way, you're basically expressing the same things. You're expressing, I would like to have all entities that have a minion velocity on it. And if you put multiple on here, if we put like a rotation speed value on it, then you're saying, I want a minion velocity and a rotation speed, and call my execute function for each one. So it kind of gets us a little bit closer to this more object-oriented way of thinking while getting exactly the same performance as if you wrote it completely data-oriented design style. And we're going to probably put some more effort into sort of like getting more into this way of writing code so that it gets really, really easy. If we look at a bit more complicated example, so this is similar to when the minions in the bigger demo, when they were exploding, when we hit a fireball on them, we basically destroy the old entities, we create new ones, and we basically have sort of a tiny rigid body system, right? Because if you're running 100,000 objects, you don't want full rigid bodies on them, right? We're not trying to make them fall accurately. We're just making sure that when they hit the ground, they stick around for a couple of seconds and then disappear, right? We're keeping it simple. We want crazy-ass massive scale. Here we have our job. We fill out an array of raycasts, basically. We have the velocities for each of these minions, and this raycast job is responsible for filling out each raycast command. So we have the position, the velocity. Based on that, we know how long it will travel. So that's the length of the raycast. Then we schedule that job. We get the dependency back. Then we fill out a second array, and we let the raycast system fill it out for us in a job. And we put a dependency on the first job, right? Because we want to make sure that this array has been filled out before the raycast runs. And that gives us back another dependency. So now we have a job performing the raycast, then a job filling out what raycast to do, then a job performing the raycast, and then we can have a job that reads the result of the raycast and applies it. So then we have another job here. This is where I put removed the dependency earlier. We integrate that back in a job. So then it looks like this. Basically, we just check, did the raycast hit? Okay. If it didn't hit, we just move it forward based on what we wrote into the input raycast, right? Based on the direction and the distance, we move it forward. Otherwise, we just stick the unit at the position where we did hit with the raycast. And then we apply it back into our array. And basically this way, we have written code that runs completely asynchronously to the main thread. Basically, this system, the onUpdate function, it only schedules jobs. It doesn't wait on anything at all. If there's somebody before mutating the velocities, that's fine. We're taking a dependency on that system. And we're just running it a bit later in the worker threads. Okay, so that's basically how the different job component system look like when you write jobified component system code. So the next part is about the C# job compiler. So the C# job compiler is where we get really, really significant speedups on top of just getting multi-core speedups, linear data layout, and so on. We want to also make sure that we have a compiler that is that generates code where if you write, if you compare it to C++ code, we can significantly beat that. Assuming you're writing normal, maybe you have a math library, a high-level math library with SIMD code. If you do that, our compiler will generate better code. The way it works is you simply put an attribute, compute optimization, on it, and then you can specify what precision you want, for example, for your jobs. And this compiler is only for C# jobs. So what is good about that for us is that it means that we have to solve a much simpler problem. Because in these C# job systems, there's already a lot of rules. For example, we don't have virtual functions. We don't have reference types. There's no garbage collector. There are only native containers. And all we really care about is making that code run incredibly fast. And so basically, we have a team that is very focused on just performance as opposed to making everything work. So these are some of the results we get from these optimizations, and that's part of that is automatic vectorization of the code. Part of that is just inlining all of your code into basically a single function and executing it all together, and that exposes a lot of ways in which we can automatically vectorize your code. And generally what we've seen is something between 5 to 15x speedups so far. So that's really, a lot, I guess. I mean, it is pretty crazy, the kind of speedups we get. There's a lot of cool stuff you get with it. Like, for example, you can control at what precision your math functions work. If you call a sinus function, maybe you don't need 32 bits of precision for it. Maybe you're just animating a massive army of units, and it's okay if it's off by 1 degree or something like that. You can make that choice at the in the compiler. You just basically write something like this: compute optimization, and then you say precision medium, and then it will compile code that has less precision. So a big part of getting that performance in the new compiler is that we also want to introduce a new C# math library. So this C# math library looks a lot like HLSL. So we have float1, float2, float3, float4, half values to make sure that your data is really tightly packed. And then all kinds of utility methods that you're used to if you know how to write code in HLSL. ABS, power, min, max, clamp, and so on. And you also have functions like math.select, which you can use to write branch-free code. So select is a function, for example, where you can feed in a bool, and then it selects between two different values. And that is one way in which when you write automatically vectorized code, you can get quite some significant speedups. So basically there will be a new math library that you can use, but you can also use the old one. But if you use the new one, there's a lot more we can do with performance. And then the last question is, of course, when does all of this ship? So the C# job system ships in 18.1, and that includes the native container library. And we're also releasing the entity component and the math library with full source code. So we will give those out as a project folder. We'll have it on GitHub so that you can check it out and play around with it, because we want to really get a lot of feedback on it and iterate on it a bit more before we really bake all these new concepts, because it's really a completely new way of writing code in Unity, and we want to really make sure that it's right, and we want to get a lot of feedback before it's really fully baked into the engine. The code itself, though, the entity component system, it's pretty robust. It just isn't as integrated, mainly because there's this game object entity thing you have to put on each game object for it to show up in the component system. But otherwise, it's pretty solid. And then the C# job compiler will ship later in 2018. So that's it. So now, if anyone has questions, we'll take questions.
So I'm a fan of the entity framework, even in its current state. Mm-hmm. Not so much of a fan of just forming dependencies of one class to the other. So like currently I'm using like a dependency injection frameworks, went through several so far. Right. This is a lot to take in, you know, I'll probably watch this again. But how do you, like, has anything changed in terms of interdependencies of multiple classes in like more classic OOP style programming?
Well, yeah, so I mean, one thing that we definitely want to bring to mono behavior or a new version of a mono behavior for the people who want to continue to write object-oriented code is dependency injection. Because it's, you know, when we start writing more and more of this code, we need a lot of managers and systems. Yeah. And dependency injection works really well for that.
So you're planning on implementing that natively?
Yeah.
A framework? Oh,
we want to do that, yes.
Do you know when? Later, 2018 also,
well,
or?
So for now, we just integrated it in this entity component system, so all the component systems have dependency injection. But
right. Yeah,
when it will ship in a new mono behavior, that's we'll figure that out.
Okay, great. Thank you.
You're welcome.
Hi, I'm from Audiokinetic. We make Wise, and basically I have some concerns related to native plugins and how all this would essentially be how we'd be able to take advantage of it also, or whether we'd be able to.
Right. Well, basically, the great thing about this new compiler tag is that it doesn't need a GC. So for audio specifically, because it doesn't use a GC, that means there will never be any stalls. So it makes it really feasible to actually write all of these audio code or audio plugins in C#. And we're also working on a new lower level API for audio that you can use to basically plug C# into, plug sort of like these C# jobs into it as audio jobs, so to speak.
Well, I was more so thinking related to accessing the was it the
Native arrays?
the native arrays and the native containers, exactly.
Yeah, so so for interop, it makes it really easy because you can, if you want to, you can get an unsafe pointer to the data. So then you can basically get direct access to the data without copying it.
Okay.
That makes interop with C++ much easier.
And then also you have a transform access array.
Yeah.
Is there going to be any ability to have similar functionality for other custom classes?
Right. So that's the, I mean, we do want to expose more and more of the engine with sort of like native arrays and these primitives where there's less copying going on.
Exactly.
That's still kind of like the open question. I mean, I predict that what we'll do is we will probably rewrite a lot of components, and we will rewrite them in C#, and we'll expose really, really low-level functions that are actually not component-based from C++. As an example, that's how we do navmesh. So navmesh, we just have a navmesh query buffer, and you can do pathfinding operations on it, and you can use it from a job. But then the navmesh agent is actually written as a iComponent data. And that gives a lot of flexibility to the user because, you know, if you want to do a formation system or something like that, very specialized, you really need to control pathfinding and sort of like how to stay on the navmesh polygons yourself in a very tight way. Mm-hmm. And that approach really makes that much more feasible. And I think it actually makes sense for almost every subsystem to do it that way, given that we have this new system. So we'll probably move more code, the component implementation into C# so that you can actually modify it.
Cool. Thank you very much.
You're welcome.
Hi. You're saying that this ships in 18.1.
Yeah.
But if we wanted to familiarize ourselves with the workflow, is there a broken version that we can play around with?
Yeah, so we will, this year we will ship preview builds of it.
Awesome.
And we will start on that pretty soon.
And then the other thing was, you mentioned earlier that the enemies don't have game objects.
Right.
Could you talk a little bit more about that? Because I'm not sure
right.
how.
So the idea is that this new component system that we wrote, it's like you can think of it as a parallel universe of a new component system. And this game object entity component is basically what injects the old game objects into the new one so that they are visible to it. And in a new system, there's no game object, there's just an entity, right? Like, we don't really deal in game objects anymore. And that's, if you want really massive scale performance, and you also want to make load time massively better, right? If we want to improve load times by a lot, then we have to read that data, we basically have to not do any serialization. We have to just copy some data over, and then that's your component data, because all the data is now blittable. So it's like creating these new super lightweight components is kind of the way forward for us to get really, really big speedups. And for you to write code that is just as fast or sometimes faster than C++ code doing the same thing.
Awesome. Thank you very much.
You're welcome.
My question would be about using components like sprite renderer on an entity, or can you use basically any Unity component, or is it just specific components?
So the component system supports any type of component, right? Like, as long as you put this game object entity component on it, then it will be visible.
Okay.
And that gives you main thread access in a component system. But since it is a class, the sprite renderer is a class, you can't use it directly from a job. What you can do is you can just write to some of your own data and then on the main thread apply it back. So right now, the only C++ component you can talk to from the job system is the transform.
Okay, thank you.
First off, I want to say thanks for working so hard and making a really awesome system. I think Unity's changing the world, and I'm a huge fan, and this new API looks amazing.
Thank you.
So I'm really interested in the integration with the physics system.
Yeah.
And you talked about how there's that custom raycasting for the ground detection and stuff.
Yeah.
If one were so inclined to write a complete rigid body simulation that does accurately solve collisions and that kind of stuff, do you think it would be faster and better than NVIDIA's PhysX?
I think so. I would love for someone to take up that challenge, because there are so many. So actually, physics is extremely well suited for this, because usually, you know, when you write physics code, then there are so many algorithms in there that it's very difficult to perfectly write vectorized code in C++ for it. Right? So for example, PhysX, they use a vector library, but it's far from the most optimal way of writing vectorized code. And I am pretty certain that our compiler would do a much better job of generating fast code than you would get in C++ in this particular case. So that's one thing, that I think you would get better performance out of it. Then the other thing is, you can just develop it relatively quickly, because there's a powerful math library, there's a job system, and there's a component system, right? So you basically just have to worry about the algorithms. Whereas usually in a physics engine, you have a lot of memory management and all kinds of stuff to build. That's one thing. And then I think there's another really killer reason, and that is, let's say you wanted to make a physics engine that is deterministic across multiple platforms. One thing that we want to do is, in the C# job system, we can, just like we have these attributes for lower precision, which would be also really awesome for physics. I mean, sometimes you care about high precision physics, sometimes low precision physics, and you just change an attribute on it and it runs faster. But one thing we want to add is deterministic compilation, so that we can, on an ARM machine and an Intel machine, we can generate deterministic bitwise exact code. So you could use that if you want to make a network game where you want to do massive scale simulation and do lockstep simulation. That would make that really, really simple. And there's no physics engine today that does that, because it's practically impossible to do in C++. But with the compiler, we will just have that as an attribute at some point.
That's incredible. I've written a GPU-powered physics solution in Unity, and you think the CPU-based one with the C# job compiler, it would exceed a GPU-based, likely because you wouldn't have to transfer the data between the CPU and the GPU?
Well, it depends. I mean, I guess if you do a GPU-based physics simulation, then I guess the best way to do it is to connect the rendered objects directly on the GPU and not go back to the CPU.
One last question. I noticed StarCraft in your applications directory. What race do you play? And do you want to play some twos sometime?
I play Terran.
Me too.
Cool.
Sweet.
Awesome. Do that physics system. It will be awesome. Yes.
Hi, this is really interesting stuff. Somebody else said a lot to take in. Working in the non-game simulation space, this has some real interesting potential for that. My question is, with respect to dependencies, I'm interested in what I'm seeing from the way that the dependency injection happens. My question is, when it comes to debugging that in terms of performance, where there can be basically nested trees, fairly complex nested trees of dependencies that can emerge in the job system, and seeing your code and visualizing those across multiple files of code could get to be fairly complex. Have you guys given any thought, and do you have an idea of where you're going with respect to two things? One being static visualization, some kind of a tool that looks at the code statically and maybe renders a graphical representation of where your dependencies are.
Right.
And then part two of that, and I realize that at the performance scale we're talking about deep instrumentation. Sometimes you get into a Heisenberg problem where you're instrumenting it and you influence the performance because of the instrumentation. but is there a plan for some sort of instrumented execution mode where you give up speed, maybe scale time down or something like that, give up speed, execute that, and have some way of visualizing where the wait states are, when you hit one of those complete calls or an implied complete, where the wait states are, so that you can figure out if your code's not as fast as you thought it should be,
yes.
where that was.
Let me just bring up the timeline profiler. So the first, the natural, it kind of, okay, it's great. The timeline profiler, basically shows you that. So if you do a wait on the main thread, it will show you that it's waiting. Right now, it doesn't visualize exactly what it's waiting upon, but we will pretty soon start drawing some lines to the job that is actually waiting upon. That's one thing. And we're already, extracting that data is pretty simple. And I think exposing that in a graph way of looking at it so that you basically see all the dependencies between jobs would be really powerful. What would be even better is if it showed you the dependencies that you put and the dependencies that are necessary based on the data right now. Because then, sometimes what actually happens when you write game code is you put too many dependencies, and that can reduce your performance because you put additional weights on it. And we could visualize when you put too many or too little, and we can just give you an overview. And that's, because of the way we've built it, that is actually really easy to extract out and visualize.
Thank you very much. It sounds interesting.
You're welcome.
To follow up on the physics queries, would we have a parallel universe version of all the old physics calls, obviously all the ray casting stuff, but sphere cast, line cast, even compute penetration and the overlap stuff?
Yes, we have those.
And would we also have parallel universe versions of the old colliders? Maybe we don't even need a collider component, we just have a structure that's sphere collider structure.
Yeah. So, how we move those things over, right now we have just done it for NavMesh. And with NavMesh, we have basically really we just have a very simple C# sample code, so to speak. Or, it's a built-in component, but it basically acts as sample code of how to use the low-level API. And then all of the code is available. And I think that approach of actually moving, maybe exposing the low-level physics API and then building the component system in C# on top of it, that is the most powerful way of doing it.
Thanks. And would you maybe have some, when you release this first versions of this, have some of the examples, maybe not the RTS demo specifically, but examples called from that?
Yes.
We will driving animation and things.
Yeah, we will absolutely have a lot of samples. I think that's very important in making this thing a success, that people can see exactly how to write this kind of code.
Excellent. Thank you.
Welcome.
So in C#, structural value types, and are you boxing all the entity data when you actually derive from the interface?
No, there is basically what we do, that would kind of defeat the purpose, right?
Right, yeah.
What we do is there is generic extension methods in C#, and with those you can do all of what we did without any boxing.
Oh, okay. Nice. That's it.
It sounds like from everything you've been saying is that that your the new managed system is beating C++ code and those type of things. But is there anything with this new system that's is being hindered by the fact that it's still C# managed code?
I actually think that it makes it better to be in C#. Because I think that, if you write multi-threaded code in C++, I don't know how I would approach building a safety system for that. And I think that safety system brings a lot of the simplicity that makes that approachable. And I think it does it more so when you write multi-threaded code rather than without. And because we can actually restrict the usage in C# because it's a more controllable language, and because we can do post-processing and we can write our own compilers against this bytecode and these kind of things. It gives us more control to enforce a model that really enforces performance in a really good way and that enforces safety. And so I actually really do think that, I mean, it's just better to write high-performance code like this than in C++.
Awesome. Can't wait to try it out.
Yeah.
I'm actually just curious. A lot of this stuff reminds me of like how I wrote code in CUDA, like converting, arrays of structures to structures of arrays. My challenge there is when I ever have to shuffle or like sort, and I was just curious how you, like the solution you've come up with. Like for me, it was just like copying buffer or temporary buffers, but
right. Well, the big difference is that we're still running this on a CPU. So if we want to sort some, you asked about sorting, right?
Yeah, shuffling, sorting.
So you just do sorting exactly like you do it now. I mean, you can write normal CPU code. Just because you have now the option of writing branch-free code with math.select and all these things, doesn't mean you have to. I mean, it will just not be very vectorized if you have a lot of branches in your code. But it's running on a CPU, so.
Okay. All right. Thanks.
And it will still, like even in cases of sorting, the compiler will still find a lot of stuff and get some pretty big improvements over other C# code.
Thank you.
I think it's really cool, and I like what you guys try to do, so that's awesome. I've read some stuff about data-oriented design. I think that's what it's called. Yeah. And in my mind, it's amazing, but I always think, but it's only amazing if you have a big team, if you're kind of a small team trying to manage all that. And it sounds like you guys tried really hard to make it manageable for a small team.
Yes.
But I was kind of thinking, what made you take this approach versus trying to do something like in a monobehavior, like linked update, where the transforms between all the game objects of the same type could still be read in memory, like you were saying, sequentially?
Well, I mean, I tried that for years. Well, I mean, I don't know, maybe I didn't try hard enough. But I guess, I think it's difficult to go halfway with performance for myself because it's very difficult to compare when you're actually done or when something is good. And the problem is when you have this object-oriented style of writing code, then there are always, some holes, like, like your memory layout is all over the place. And so you're always, 2 to 3x slower at least. And it just makes it very difficult to, I mean, I don't know, I just think it's better to go all the way with performance, and then, like we basically started out by writing the C# jobs, and we just had native containers. And then we built the entity component system. And I think we're pretty good at figuring out how to make components easy to use and how to make it easy for game developers to write code. And that's what we can do now. Like we just take this approach with which you can get the best performance. And now it's about how do we make it really, really easy and simple so that anyone can do it. And that's really, the safety system is the first part. The second part is sort of like these more automatic jobs where you basically just have the system as the job and you don't think about dependencies and these kind of things.
That makes a lot of sense. Cool.
Thank you. This is very cool stuff. I have one kind of specific question. Are you familiar with, actually, any game with RPG element? There's in any game with RPG element, there will be complex skills.
Complex what?
Skills. Spells.
Oh, RPGs with complex spells in it.
Yeah. So, for example, even StarCraft 2, it has complex skills for those units.
Yeah.
I think there are ways to do data-driven design with a lot of graph editors kind of stuff. So in this way, it's basically calling for a system that can handle many kind of data, which might not be suitable for structs. Do you think this kind of thing can benefit from this system?
Right. Yeah, I mean, generally I would say any problem can be expressed object-oriented and any problem can be expressed data-oriented design style. In some cases, writing object-oriented code is a lot easier and much less code and much easier to understand. In some cases, data-oriented design code can be simpler. But I think it's just a question of, I mean, you look at the specific problem and sometimes you just rewrite it in a slightly different way in data-oriented design and you get great performance and it's actually not that hard. And sometimes things do get hard. I mean, you use, when you do data-oriented design style coding, you use a lot of indices, you don't use pointers, and sometimes that can be harder. But you're trying to, I mean, at the end of the day, you're trying to solve a problem, right? I mean, like, you don't have to use data-oriented design for everything, but if you want great performance, then, you'll have to do something for it.
Sure. Another thing is the job compiler. Does it support IL2 CPP?
So the C# job system can run in mono or IL2 CPP, or also in the new compiler. But the compiler is basically, for that code that runs in a job, it replaces the code, the IL2 CPP code.
Okay.
Right? It's, yeah.
Thank you.
You're welcome.
Hi, thanks. I guess my question is, so the job compiler or the burst compiler, so the code that you write for that, is that going to have to be in like a separate folder or something? Is like a first pass that it goes through that compiler, then any mono behavior stuff would go back to the mono compiler, or is this basically everything's going to go through the job compiler?
No, I mean, the great thing about it is basically it's all just C# code, and it just happens to be a struct with an iJob attribute. And then when we schedule it, that is actually when we make the decision on if we're going to run it through the C# compiler, the C# job compiler, or through mono. Because of course, you very often need mono, because then you can single step through the code. And that's super important. But then basically we can just at schedule time determine which compiler we use, and then at build time, you can use it. But it's basically completely automatic. You put your struct wherever you like. I mean, in most of these component systems, I actually put the job struct into the component system,
Okay,
like as
so
a substruct.
So this will build out to like just the same DLL, it doesn't actually need to split them out or
Exactly.
anything? Oh,
Yeah.
sweet, thank you.
For machine learning purposes, like self-driving cars, using LiDAR simulation usually revolves around either raycasting or using a depth map from graphics to try to get the picture of the world.
Yeah.
At my company, we ran into get pixels was quite slow to get a texture. We started using async get texture, which was an open source GitHub repo. And we're trying to basically have a C++ plugin pull textures directly out of GL or DirectX. So when I heard about the programmable graphics pipeline and the C# job system, I thought, you mentioned it could actually do raycasting. So in principle, you could go back to like raycasting every pixel with enough cores and throw power at it that way. But
yes, but there's also a compute shader-based async readback function in 17.3 or 18.1.
That makes my day, because I've been using an open source GitHub repo to try to do that. So it's going to be built into Unity?
Yeah.
Fantastic. Thank you.
Welcome.
Hi, I'm curious about how you specify the memory allocation. Like you said, you could like switch between different modes. So you've got either contiguously doing your whole entity or component or doing parts of it separately. You had the visuals on the slide. So how does it actually work? How do you specify that?
How do you specify the
how do
layout of the
Right,
component data?
Yeah.
Right, you essentially, you define sort of like stream groups. So you specify, I want component A and B to be in group in group 0, and then component C and D in group 1, and then they basically get grouped together.
And that's part of some configuration it's not part of the code then?
Yeah, so basically there is a, like what I showed is like creating entities from prefabs, but you can also create what we call an archetype. So an archetype is a set of components, and it also defines the layout of all the components with the same set of components. Okay. And on that you can specify the layout of the data.
Right. Have you thought about a process where you would like automatically profile what the best layout is and optimize based on that, like a magical button?
I did.
You did?
I bet someone on the asset store will do it.
Yeah.
But if not, then we'll do it. I don't know.
Yeah,
but
well, it sounds like you can get that information so you can optimize it. So yeah,
it would be brilliant, right?
Perfect. It would, yeah.
It's also pretty cool. There's we have the player loop fully exposed, so you can reorder the player loop. And that's of course super important, right? Because when you write jobified code, the important part is when do you schedule a job, when do you wait on the job. And that's actually the player loop, right? Let's say you have the animation system mutating a transform data, and then the bounding volume updating before rendering reads that data. You want that amount of time to be as large as possible in the frame. And often in a game, you can actually change the player loop quite a bit without breaking the game. So that could also be automated. So these things, I think profile-guided optimization for that would be really applicable.
It's a great area, I think, for helping improve performance without a huge lift. So great, thank you.
So I was thinking in terms of so we have this new entity component system, but all these things, they're no longer game objects, you know. So in terms of how it's rendered, you have this new entity component renderer, or
yeah. So what we did for the demos we wrote is we wrote one in C#. I mean, we have an API called graphics.drawMeshInstance.
So you just use the basic from the CPU just scheduled all the jobs manually each frame?
Exactly.
Okay.
And that's actually a really efficient way of rendering it. We will think about how to do sort of like a built-in renderer that fits into the new system, just like we have to do for physics. I mean, as a starting point, we're just starting with C# only, and then we'll just start moving more and more into that system so that you can write these really tight entity-only components.
Awesome, thank you.
Besides moving to a design-oriented, data-oriented design, do you have any tips for teams that might be starting production or just at early stages that would like to jump on this as soon as it's available?
I don't know. I think we'll probably have builds in 1 or 2 months. I'm not sure what to do in the time in between. Yeah, watch the time. Okay, for times, that's a good one.
Thank you.
But yeah, that said, I don't know how to help with that. Yeah.
Hey there. How about debugging through this system?
Right.
With the entity component system.
Yeah. So the entity component system, like how to debug it visually, you mean?
Yeah. So in general, if you wanted to step through code and stuff like that. So.
Right. So if they are the pure entities and not game objects, right? Because usually use the game objects in the inspector to look at what the state of things are. Right. So we will make tools that show entities even though they're not game objects.
Okay.
And there's interesting ways of visualizing that data now, right? Because we can say, let's look at it from the perspective of each component system. How many are there in each component system, and so on. So I think we can actually make these tools even more powerful than what you now have for debugging.
Okay. Thank you.
You're welcome.
So when do we get nested prefabs?
Nested prefabs. Bam. Well, we actually have a solid team working on it, and they have been gathering a lot of feedback and so on, but I mean, that is shipping in 2018. Yeah. All right, it appears that were all the questions. Thank you so much.